Hello friends, in this video we are going to discuss pure iron phase diagram in thermodynamic sense. Why these curves are like this, why the slopes of some curves are positive, some are negative, and after this we are going to discuss the cooling curve of iron. Friends, before starting the video I want you to tell me what exactly are you preparing for. If you are preparing for GATE, I'm going to make videos for that. If you are preparing for interviews, I'm going to make videos related to that. So please do comment what kind of videos are going to help you the most. So friends, let's start our video. Let's look at all the forms in which iron exists, all the allotropic forms of iron. So friends, basic crystal structures that are possible for iron are BCC, FCC and HCP. So friends, but if you look at all possible transitions, these are all these five. Alpha ferrite, which is magnetic ferrite, and when it reaches a temperature of 768 degrees centigrade, it converts to non-magnetic ferrite. And we have austenite, hexaferrum is HCP iron. I'm going to discuss more about HCP, how we get HCP iron, and delta ferrite. Out of these four, 1, 2, 5, these three are having BCC crystal structure, and austenite and hexaferrum are having FCC and HCP respectively. Friends, for pure iron phase diagram, x-axis is pressure and y-axis is temperature. So the slope of this line is given by dt by dp. But friends, in one of my previous videos, I have discussed an important equation, Clausius-Clapeyron equation, which gives us information how the transformation gets affected by the pressure. So friends, this is our Clausius-Clapeyron equation. The rate of change of transformation temperature with pressure is given by the change in volume divided by the change in entropy. So friends, now let's discuss the transition from one phase to the other phase. Friends, here to avoid confusion, we go from low temperature phase to the high temperature phase for all transitions. So let's start with our alpha ferrite changing to the austenite, gamma. So here friends, we're having alpha iron, BCC transforming to the gamma iron. So friends, on increasing temperature, BCC is changing to FCC. So friends, we know the packing fraction of BCC is 68% and FCC is 74%. So friends, here, please look carefully. The packing fraction is increasing. So what is happening, friends? Volume of BCC is decreasing, right? So volume of BCC is going to volume of FCC. Which is greater here? BCC is greater than FCC. So because of the packing fraction. So friends, here the delta V is negative because the product minus reactant. So the delta V for BCC to FCC is negative. So friends, if we consider the entropy of any substance increases with temperature. So delta S is entropy of gamma minus entropy of alpha, which is positive. So friends, when we use our Clausius-Clapeyron equation, we get dt by dp is equals to delta V by delta S. We got delta V is negative and delta S positive. So which is negative. Which means, friends, for the transformation of alpha to gamma, the slope of the equation, the slope of this curve is negative. So we can see this, its slope is negative. Friends, for the same, if we consider for gamma to BCC, delta V is positive and delta S is negative. Either way, the change of transformation temperature with pressure is negative. So in our phase diagram, this curve has negative slope because of the Clausius-Clapeyron equation. So friends, let's consider our second transformation where FCC is transformed into the delta, gamma is transformed to the delta. But friends, here the opposite of the earlier one, right? Here FCC is transformed to BCC. BCC is having low packing fraction, so here delta V is positive. Since we are heating, so delta S is also positive. So here we get dt by dp is equals to positive by positive, we get positive. So this curve is having a positive slope. So friends, if we consider the transformation of delta to liquid, of course liquid is having more volume and entropy is also more for liquid compared with the solid. So here also we get dt by dp, slope of the curve is positive. So this curve is also having positive slope. So friends, now we're going to discuss the transition from alpha to HCP and gamma to HCP. So friends, if we consider the transformation of alpha ferrite to HCP, on heating our alpha transforms to HCP. So friends, here just like FCC crystal structure, HCP is also having higher packing fraction than BCC. So here the volume is actually decreasing because we are going from 68% to the 74%. But delta is S, as temperature is increasing, delta S is positive. So here we get dt by dp is equals to negative. So the slope of this curve is negative. Hello friends, here epsilon and gamma both are having same packing fraction, but delta S increases with increasing temperature. Entropy always increases with increasing temperature. But which of these having more volume? Friends, here we need to understand, even though both are having same packing fraction, as the temperature increases, the unit cell increases, right? Because of thermal expansion. So even though both are having same packing fraction, since gamma is at higher temperature, its volume is more. So here delta V is product minus reactant. So since gamma is having more volume than epsilon, we get this as positive. So same friends, dt by dp is equals to positive. So the slope of this is positive. So friends, all these questions are very important, as an interview point of view. So please comment if you have any doubts. I would be more than happy to reply. Friends, now let's discuss the second part of the video, cooling curves of our pure iron. So friends, before drawing the curves, let's discuss what are all transitions possible at room temperature. We are starting with the liquid. So friends, the first transition is liquid transforms to the delta BCC iron at high temperature. So friends, then delta transforms to the austenite. Then friends, austenite transforms to the ferrite, which is non-magnetic at 768 degrees centigrade. So friends, our final transition is non-magnetic to the magnetic ferrite. So friends, let's draw our cooling curve for pure iron. So we're starting with liquid. Liquid, very high temperature at here liquid is transforming to a delta iron. So friends, at the transformation temperature, with increasing time, temperature is constant because of the recalcitrance heat. The material gives enthalpy of liquidization. Here the material gives up that amount. So here, even with time, even though we are extracting heat, the temperature stays constant. So this is our first transition, friends. Liquid transformed to our delta iron. So friends, this is done. Now our next transformation is delta transformed to the austenite. So delta is cooling at this temperature. Delta transforms to the austenite. And this is done, friends. Next, austenite transformed to the magnetic transition. So here austenite cools down. Then during the magnetic transition, there is again some amount of heat release. Here friends, gamma transforms to non-magnetic alpha. Then friends, this is our final transition occurs here. Then it cools normally. Our final transition is, so friends, at 768 degrees centigrade, our alpha non-magnetic transforms to the alpha iron. So this is our final form. Friends, here we don't have the epsilon or epsilon HCP iron transformation because of we are doing this at atmospheric pressure. HCP iron forms at a very high pressure of order some 10 gigapascals. At this very high pressure, since HCP is having more close packed structure, BCC is having some voids which gets crushed and it turns to HCP iron. This actually happens at very high pressure points like at our core of earth and these criteria. At normal temperature, we can never have HCP iron. So this is in this video, guys. This is the cooling curve. I hope you understood the concept. If you have any doubts, please feel free to comment, and any concepts which you would like me to discuss. Thank you so much for watching. If you like the video, just comment and like the video. Please do subscribe. Have a nice day.